Good afternoon. This is our sixth lecture, and we have already started our discussion on the governing equations for multiphase flow problems. Okay. So, if you recall, yesterday we discussed about the different forms of continuity equation for multiphase flow problems, and we briefly started our discussion on the conservation of momentum equation. Okay, so if you recall, in conservation of momentum equation, this right hand side first term represents the time rate of change of momentum of nth phase within the control volume, and second term represents the rate of change of momentum of nth phase across the boundaries of the control volume. Okay, and this must be from Newton's second law of motion. This must be equal to the net force, total force. So T, this F superscript T refers to total forces, and this N refers to nth phase. So all the net forces acting on nth phase, and K represents over here kth direction. So it means this particular momentum equation we are writing in nothing but kth direction. Okay. Now, whenever we have to consider the forces, we will be having three different types of forces. One will be body forces, other will be surface forces which are acting because of the boundary effect, and third type of forces will be interaction from one particle to other particle. Okay, so or in other words, I should say that from the other phases on the nth phase which we are actually considering. Okay, so this is our first term, which is nothing but body force. So this body force is rho n, density of nth phase, into gk, where gk represents the gravitational pull in kth direction, and this alpha n is used because entire mass of the control volume is not comprising of nth phase, rather it is only having alpha n volume fraction. Okay, then to account for the surface forces, okay, to account for the surface forces at the boundary of the control volume, we have this term del by del xi into sigma c ki. So over here, whenever I am referring to term sigma c, so c is at the boundary. When we are calculating the surface forces due to different stresses, we are only considering the stresses because of the continuum phase. Why continuum phase? Because yesterday we made one assumption that whenever we will be deriving the momentum equation, if any dispersed phase particles are present at the boundary, we are considering that boundary of the control volume is deformed slightly, so that throughout the entire boundary we have contact of the continuous phase only. So because of that, whenever this stress element we will be writing, the stress tensor we will be defining it based on the continuous phase only. Okay. Then this sigma ki, typically as we do in case of fluid mechanics, so in our stress tensor there is contribution of the two things. One is because of the normal pressure, okay, and second contribution comes because of the viscous effects, and particularly the contribution which is coming because of the viscous effect, that is called as deviatoric stress. Okay, so that's why sigma cki I am writing as minus p into delta ki. So this first effect is contribution of pressure. So contribution of pressure will always be acting in direction normal to the phase. Okay. Whenever you calculate the deviatoric stresses like stresses because of the viscous effects, these stresses can act in both the directions, normal direction as well as parallel to a boundary. On contrary, the contribution of pressure will only be coming normal to the boundary. So that's why whenever I am writing this minus p, I am also writing delta ki over here. What is the meaning of delta ki? Delta ki is once again a Kronecker delta operator, and this will be equal to 1 only if my k is equal to I, and it will be equal to 0 for all k is not equal to I. It means if k and I are equal, I am referring to a kth surface as well as the kth direction. Okay, so it means I am referring to normal direction to a surface. Okay, is this point clear? Or let me show you. So if you have a control volume like this, and if these are your directions I, J and K. Okay, so typically how to designate a surface? So what we do, if this is my surface, if normal to this surface my direction is K, then I will be calling this as nothing but my kth plane or kth surface. Okay, so if my plane and the direction in which force is acting, for example pressure is acting in downward direction, if both are same, then only this first term will be actually coming into picture, because pressure always acts normal to the face, it cannot act like this. Okay, so that is the reason, to account for the pressure force, I have multiplied pressure term with a Kronecker delta. Is this one clear? Then we have second term, so sigma CKIT. So this is sigma for continuous phase, and particularly this superscript D represents that here we are considering the deviatoric part of the stress tensor. So deviatoric part is nothing but the part which comes because of the viscous effects, that is called as deviatoric part. Okay, and particularly if you talk about Newtonian fluid, then this particular stress tensor will be having three normal components: 2 mu into del u by del x, okay, 2 mu into del u by del y, 2 mu into del u by del z, and there will be three symmetric shear component. Three symmetric means 6 in total. Okay, so these will be nothing but mu times del v by del x plus del u by del y in tau, that is nothing but equal to tau yx or tau xy. Okay, so likewise at the moment I am not specifying it for a particular fluid phase, but whenever we will be discussing this particular course of multi-phase flow, we will be only talking about the Newtonian types of fluids. So that is the kind of within the horizon of this course. Okay, but there can be situations of non-Newtonian multi-phase flow, so that is beyond the scope of this course. Okay, so this deviatoric component, particularly for Newtonian fluids, it comes nothing but from Stokes' hypothesis. Okay, and then it is represented in terms of the dynamic viscosity. Okay, so all of you know that. So if you are forgetting at the moment, then please revisit your concepts of momentum equation, particularly Navier-Stokes equations for single phase flow. Okay, is this one clear? So this is normal component and this is my deviatoric component. Okay. Now what I can do, I can substitute all these terms in place of Ft and K. Okay, so this right hand side is now over here. This is the first term, this is the second term. So these two terms are taken as it is from this first equation, and in place of F and Tk, now I have written this first term which is my body force. Then I have written this another term. What is this term? Del P by del X K. So this is pressure gradient in kth direction. Okay, and this pressure gradient will be only applicable where? Ultimately, this equation, whenever I am writing, this is becoming nothing but individual phase momentum equation. What is this? This is my individual phase momentum equation. So whenever I will be talking about the individual phase momentum equation, in case of individual phase momentum equation, these surface forces should become active if and only if I am considering that particular phase. So that's why I have used over here Kronecker delta operator with subscript n. The meaning is, say if I am talking about dispersed phase D, so when my n is equal to D, in that case only this will be equal to 1. Otherwise, if my n is not equal to D, then this will be equal to 0. Meaning is clear? It means when I am writing this particular equation for a dispersed phase, then this will be active. If I write this for a continuous phase, then corresponding terms for the continuous phase should become active. Okay, all the times as this term will not be actually coming into picture. So that is the reason, and of course, because whenever we are considering the surface forces, we have to only write sigma C D K I by sigma xi. Sorry, this I have told you wrongly, because in our assumption of the equation we considered that boundary is deformed, and at boundary always continuous phase is in contact. So when my n is equal to C, then only this term will be equal to 1, and if n is equal to D, then this term will be equal to 0. Is this one clear? So for a dispersed phase, this term will not come, because why this term comes? This is the contribution of the forces at the boundary of the control volume, and at the boundary of the control volume always our continuous phase is in contact, not the dispersed phase. Dispersed phase is within the control volume. So that's why when I am writing this individual phase momentum equation for dispersed phase, then this whole term will be equal to 0. But when I am writing this equation for a continuous phase, then only this term will be non-zero. Is this one clear? Assumption, yes. Because of the assumption.
Equation dispersed phase clear. Equation dispersed phase.
This can be for both. This is individual phase momentum equation. If I consider my n equal to D, then this equation will be for dispersed phase, and delta D will be equal to 0. If I consider n equal to C, then the same equation will be applicable for continuous phase, but my delta C will be equal to 1. So it means I will be accounting for these forces. Okay. Now this term over here, you can see this is one additional term, Fn. What is the meaning of this Fn term? So if you talk about a single phase momentum equation, this term and this term are sufficient. In single phase momentum equation, what we do? We consider the body force and we consider all the forces at the surface of the control volume. But we don't consider any other force acting on the body. But in case of multi-phase flow, what is happening? Say, if I talk about dispersed phase. So dispersed phase is present in the bulk of the continuous phase. So whenever continuous phase is moving, it will try to exert certain forces on the dispersed phase. Why? Because first thing is, dispersed phase may have its own velocity. Because of that velocity, there will be interfacial shear with the continuous phase. Second thing can be, say dispersed phase is stationary, but your continuous phase is moving. So then also it will apply certain amount of force, and more important point is always we will be experiencing some sort of relative velocity between the continuous and the dispersed phase, and that relative velocity will nothing but apply certain amount of forces on the body. So one simple example is whenever you talk about in single phase flow problems, a spherical ball falling in a liquid, stagnant liquid. Okay, what we do there? We calculate the drag force acting on the body, acting on the sphere because of the fluid. So that drag force is of two types. One is form drag and second is viscous drag. Okay, what is the meaning of form drag? The drag force which acts on a body because of the difference in pressure at its faces, that is called as form drag. And drag force which is acting because of the interfacial shear, it means because of shear stresses, viscous shear stresses on the body, that is called as skin friction drag. Okay, so likewise, if you have your dispersed phase present in the continuous phase, then your surrounding liquid will supply certain forces on the phase in consideration. Okay, so this is coming the interaction forces on nth phase due to all other surrounding phases. Is this point clear? So that is the additional term which will be coming in case of multi-phase flow problems. In case of single phase flow, if your entire fluid is filled with, the entire domain is filled with a single type of fluid, then this force will not come into picture. Is this point clear? All are clear with this idea? Okay, so that's why this additional term is coming. So what I think is all of you need to revise your basic fluid mechanics concepts. Okay, please revisit, because if you are not revisiting, then you will not be able to understand. Is this one clear? What is F and K? Is this one clear? So F and K is nothing but the interaction force on nth phase due to all other surrounding phases present within the system. Okay. Now, of course, at this point, it is interesting to know what will be value of sigma C, Ki, D, and what will be value of F and K. Because till now we have not defined their values. Okay, what will be their values? That will be a challenging task in case of multi-phase flow problems. Okay. Other things too we do in case of single phase flow problems also. But how to define interaction forces? And of course, for defining deviatoric stress tensor, we will be taking the help of whether our fluid is Newtonian or non-Newtonian, and accordingly we can define the stress tensor. Okay. Now, the way we have seen in case of continuity equation, if I take the summation of all the interaction terms, then total sum of all interaction, mass interaction terms was becoming equal to 0. In a similar fashion, the sum of all interaction forces will also become equal to 0. How? Because if you say that one phase is applying some x amount of force in rightward direction, then equal amount of reaction will be applicable on the other phase. So there you will be writing, say, simple thing. If you have phase 1, for phase 1 in kth direction, if plus x amount of interaction force is acting because of the other phases, say because of the second phase, then on second phase, if only I have a two-phase system present, then on the second phase in kth direction, the magnitude of the force will be nothing but minus x. Is this point clear? So this is, for the simplicity, I have chosen over here only two-phase system to explain you this idea. But this will be applicable even for a generalized n-phase system also. Okay? Because how? Say if you have three-phase system. In case of three-phase system, if you consider that on first phase in kth direction, x amount of force is acting because of the second phase, and minus y amount of force is acting because of the third phase. Then on second phase in kth direction, because of the first phase, what will be force? Minus x. Say because of the third phase it is z. Then when you will be talking about 3k, then what will be the force? Plus y, because minus y was there, so it will be minus y because of the first, and here because of the second phase it will be minus z. Okay. Now in a three-phase system, if you take the sum of all these, then what it will be? 0. All will be cancelling out. Okay. So that is what I am telling you over here. Okay. So in a system of n phases, whatever the total sum of interaction forces will be there, that will be nothing but equal to 0. Is this one clear? Anyone is having any confusion? Yes, all the forces. Sorry? Shear force is not 0 on a single phase. What we are saying is forces, interaction forces acting on all the phases, their sum is equal to 0. Okay, you can take a simple example. Say you have a two-phase system like this. What will be happening? If this is moving at faster velocity, this is faster phase, this is slower phase. So at this interface, if you isolate your control volume including of top phase only, so what will be happening in the top phase? This will be your control volume, and this is the faster phase moving. So this faster phase will try to pull this in the forward direction. So there will be some force on the slow phase because of the fast phase. But if you consider the control volume of faster phase, then this faster phase is actually being slowed down by the top phase, so it will be experiencing some force in negative direction. So this is the force on the faster phase because of the slower phase. So their magnitude has to be equal.
इस हिसाब से तो फिर इसमें मतलब constant velocity होगी acceleration नहीं
No, there will be acceleration also.
force तो acceleration
I am writing force on individual phases. This is the force on individual phase. This is the force on individual phase. But what I am saying, sum of the forces acting on all individual phases is equal to 0. Okay? That is what I am saying. I am not saying that force acting on this phase 1 or phase 2 is equal to 0. There is some interaction force which is acting on phase 1 and phase 2. Okay? But if I do sum of all these interaction forces, then that will be equal to 0. Because whatever is the, in a two-phase system, whatever is the amount and magnitude of the force on one phase, on other phase, that amount will be acting in the reverse direction. So that's why their vector sum for the complete system has to be equal to 0. Is this point clear? So that's why you can see over here, this is nothing but summation sign. Without summation, I cannot say that F and K is equal to 0. But sum of all forces within the control volume, all interaction forces will be equal to 0. Okay. Now, it is interesting to know that if I have only a two-phase system, so in case of a two-phase system, one is dispersed phase and other one is continuous phase. So if I have a two-phase system, then whatever is the force, interaction force acting on dispersed phase in kth direction, that will be simply equal to minus of force acting on continuous phase in kth direction. Is this point clear? And this force, of course, again can be split into two parts. Like I told you, if you have a body present in a bulk of another fluid, so that particular body will be experiencing two types of forces. One is, say this is a single bubble, I am showing it in an enlarged manner. So this is the single bubble. It can happen, if this is direction K, it can happen that I have this as the distribution of pressure around this body. So this is my pressure distribution around this body. So is this symmetric or asymmetric? This is asymmetric. Okay, because we know that if I have any curved boundary in a direction normal to that boundary, fluid pressure will be acting on this. Okay, so I have plotted this asymmetric pressure distribution. So this asymmetric pressure distribution will create certain amount of force in the kth direction. So the force created in kth direction is del P by del X K multiplied with volume fraction alpha. Is this point clear? And of course, whenever we calculate the pressure force, it typically comes with the minus sign. So if you recall, go back to your Pascal's law definition in basic fluid mechanics. The pressure force acting on a body is nothing but equal to minus of gradient P. So del P by del X K is representing gradient P, and because we are accounting only for the dispersed phase, so that's why I am multiplying it with volume fraction of alpha t. So it means this is nothing but force due to pressure on dispersed phase. And of course, in other word, I can call this as my form drag. Okay? Yes, whatever I am writing now, it is applicable only for a two-phase system. Here I have one dispersed phase and other continuous. Then, second type of forces will be coming because of the interfacial shear. So say this particle is moving at some velocity udk, and surrounding fluid is moving at some velocity uc k. So because of the difference of velocity, there will be some interfacial shear. Okay, and because of the interfacial shear, whatever the forces are coming, that will be other component. So that other component I have accounted for in F dash K. Okay, but this is not only the force because of the interfacial shear. Later on, whenever we will be analyzing a single fluid particle present in a fluid medium, we will be seeing many other types of forces also. Some are called as added mass force or other terms. So what are the other remaining forces other than the pressure force which are acting on this particle? These we are actually accounting in this term F dash dk. So F dash dk includes other forces on dispersed phase due to continuous phase. So one of the simplest of this is viscous drag, skin friction drag. But other than, so skin friction drag or viscous drag will be coming into picture if I take assumption that particle is moving in a fluid at constant velocity. Okay, but if I consider the acceleration of the particle in the flow, so during the acceleration of the particle there will be other forces, such as one is inertia of the particle. Inertia force will be coming into picture. Second is one additional type of force comes into picture which is called as added mass force. So the meaning of added mass force is, say if your flow is happening in the rightward direction and if a particle is moving in the rightward direction, immediately in the vicinity of particle there will be some portion of the fluid which is sticking to the particle. So which will lead to increase in total mass which is being pulled in the rightward direction. So because of that some additional force comes which is called as added mass force. So at the moment what I am considering is I am not including the distinction whether my particle is accelerated or it is under the steady condition. So at the moment I am trying to write a generalized situation. So because of this generalized situation I have simply written F dash dk to account for other forces which are acting on the dispersed phase due to continuous phase. Okay, for different situations it can be different. In a simplest case of a steady flow of particle in the bulk fluid, this will be simply equal to skin friction drag. But if you consider an accelerated particle, then some other type of forces will also come on this. Okay, and of course these other type of forces, their importance and relative magnitude will depend upon the different flow situations which we are considering. So whenever we will be analyzing such type of particles, we will be considering whether our flow is potential flow, whether our flow is at high Reynolds number or flow is at low Reynolds number like a Stokes flow situation. Okay, so for different situations, nature of these F dash dk forces will be different. Is this point clear? All are clear with this idea? So now, if I do this little bit of tweaking with the equation, so what I have done, in my previous equation now, these terms I have actually split it. So rho n alpha n and u n k and u n I. These I have actually split it into two parts and I have applied over here the method of variable separation to find out the differentiation. Okay. So if I do so, then ultimately my equation will become rho n alpha n. So this is common term into del by del t of un k plus un I into del un k by del xi. And this entire is nothing but taking the form of Lagrangian derivative. Okay. So this is dn by dt of un. So this is nothing but taking the form of Lagrangian derivative. Okay. When you will be doing this splitting, you will get one more equation. Okay. You will get one more equation. And that one more equation will become equal to that of un k times continuity equation. No. Dispersed phase continuity equation. What is equal to? In. mass terms. Okay, so that's why I will be finding one additional term over here, u and k into in, and this u and k into in is taken on the right hand side. That's why it is coming with the negative sign. Is this one clear? So when you will be applying the method of separation of variables, okay, then one part you will be getting like this, which is equal to the Lagrangian derivative times rho n into alpha n, and other u and k times continuity equation. Okay, and continuity equation, dispersed phase continuity equation is nothing but equal to capital In. Okay, so that's why this term Ink into Un is coming because of the mass exchange. This is coming because of the mass interaction term. Okay, all are clear with this idea? So this is coming because of the mass interaction term. Is this one clear? So now this body force is same. This is the additional mass interaction term. This is the force which will be only applicable for continuous phase, and this is the interaction force. Okay, so if you see these three things, these are nothing but coupled to each other. This is equal to the total force, but on right hand side one more additional term is actually coming over here. However, this term is contributed because of the left hand side. Okay, so it means that if you have a multi-phase system, it will be having, one is total rate of change of momentum of that phase, which is represented by this Lagrangian derivative, plus there will be additional rate of change of momentum because of the mass gain or mass loss, which is shown by this term I. Is this one clear? All are clear with this idea? So simply, whenever you write for a single phase system that rate of change of momentum is nothing but equal to the net forces acting on the body. So you can simply write this term equal to all these three forces. But for a multi-phase flow system, if you are writing using this term, that total rate of change of momentum, then you have to first write total rate of change of momentum because of the Lagrangian derivative, plus loss or gain of rate of momentum because of the mass exchange, and that will be equal to then sum of all the forces. Because it may happen that you have accounted for the time derivative as well as the advection spatial derivative, but along with that, within the control volume there can be, in case of a boiling process, if you consider vapor phase to be dispersed phase, then the mass of the vapor phase is actually continuously growing. So if mass of vapor phase is growing, of course there will be growth in its momentum. On contrary, if you take a condensation process, there vapor is being converted into liquid. So liquid phase will be having gain of momentum because of the mass exchange, and vapor phase will be having loss of momentum because of the mass. Is this one clear? So to account for that, we have written like this. So this is now my, again, a different form of individual phase momentum equation, IPM. Okay. All are clear with this idea? Now what I can do, whatever my original equation was there, that was for individual phase. Now I can take the sum of all these individual phase momentum equations in order to account for, this is combined phase momentum equation. One simple attribute of the combined phase momentum equation is that it does not account for, does not include interaction terms, summation f and k. Fine. Because whenever you will be doing this summation,
Zero.
so yes, so this will be summation of first term, second term which are remaining as it is, and then you can see in case of rho and gk, now you have rho gk, where this rho is nothing but mixture density. All are clear with this idea? So in place of rho n gk, now we have rho gk, because summation of rho n into alpha n has become rho. Okay, so rho gk, and then we have removed that delta n now, because whenever we are writing the sum of all momentum equations, then we are accounting for continuous phase also. So continuous phase is also included. So if continuous phase is included, then these surface forces will always be present in the system. So that's why I have dropped this delta n over here, because now continuous phase is accounted. So that's why I have this pressure gradient term, and this is my stress tensor term. Okay, and one more term I will be getting summation f and k, and summation f and k we know that it is equal to. So this is my combined phase momentum. In this combined phase momentum equation, if I make a simplification that UNI equal to some velocity ui, okay, like all the phases are having the same velocity. In that case, this combined phase momentum equation will result in an equation identical to that of single phase momentum equation. Okay, but only difference we will be having is rho n into alpha n summation will become rho, mixture density, and this rho n alpha n will become. So this entire term will be simply replaced with rho. So if I replace this term with rho, a mixture density, this is nothing but it has become equation identical to that of a single phase flow. All are clear with this idea? So what I am saying is, if I have a dispersed phase present within the continuous phase, and if the velocities of dispersed phase and continuous phase are same, then I can solve this entire system nothing but as a single phase system by simply replacing density in the single phase momentum equation with density of the mixture. All are clear with this idea? Yes. So that's why if you have in your pipeline a number of bubbly flow situations are there where bubble size is very, very small. So in that scenario, this assumption is actually valid. So under this assumption, if you want to if you are not concerned about the individual identity of the phases, like how bubbles are distributed, what is their shape, and if your bubbles are of very small size, then most of the time, because of the dominant surface tension forces, these will be having almost the spherical shape. So under these scenarios, if bubbles are homogeneously distributed in a continuous phase, we can take the assumption of constant velocity, same velocity of both the phases, and under this scenario my problem will become very simple. I have to simply determine the mixture density, and using that mixture density I can solve my momentum equation.
स्ट्रेस टेंसर में वो शियर स्ट्रेसेस तो फिर जीरो हो जाएगा.
No, shear stresses will only come because of the continuous phase, because that is our assumption. Why shear stresses are zero?
और phases के across फिर pressure gradient रहेंगे एक single phase.
Yes. So we are not solving that part. So if I am taking that assumption, I am not concentrating on the pressure details across each individual phase. I am just looking for the pressure detail as a whole, as a mixture. Yes. Okay.
और single की बात करें तो नहीं रहेगा same velocity.
Sorry.
Single अगर same velocity है तो single discrete particle के around को pressure distribution की होगा.
Yes. If that is there can be, but these will be balanced pressure distribution with their current motion. So that will be equilibrium state of the phases.
तो सर phases के बीच में relative motion भी नहीं होगा.
relative motion, there will be relative motion, but that relative, yes, of course, if I am taking the assumption that continuous phase is equal to dispersed phase, then there is no relative motion. Okay.
तो वो return shear और return zero
Shear will be zero in between, but not at the boundary. Yes. So that's why in the combined phase momentum equation this shear will come. But whenever I am writing the combined phase momentum equation, then that shear we are not at all bothered, because that is already equal to zero. We are not bothering about that. Okay. Is this one clear? Okay. Now comes one special case. So let's see this special case. So this is the case of a uniform sedimentation of solid particles. So if I say that I have a big continuous phase, okay, and in this continuous phase I have some dispersed phase particles, and these dispersed phase particles are nothing but falling down at uniform flow conditions, okay, at the constant velocities. So if these are falling at constant velocities, then there will not be any acceleration of the particles. So left hand side of individual phase momentum equation will become equal to 0. In the right hand side, I will be only having two terms. One is because of the body force of the dispersed particle, and second term will be because of the interaction force on dispersed particle due to the continuous phase. Is this one clear? Not clear? Okay.
zero कैसे होगा?
Okay. What does this term represents? This is local acceleration. This is convective acceleration. If I take the assumption that I am having uniform flow sedimentation, it means that these solid particles are falling at the constant velocity. If these are falling at the constant velocity, then acceleration of the particles will be 0. So that's why for dispersed phase, if I write, then for dispersed phase my left hand side will be equal to 0. Is this one clear? Then second part is, in the right hand side I am having now three set of forces. One is body force. So body force I have written over here. Second is interaction force acting on the dispersed phase because of the surrounding continuous phase, that is FDK. And third is surface force. No, form drag, and this is now included. So form drag I was separating when I was using symbol F dash. Now F is including all. So including all interaction forces, and then third was surface forces at the boundary of the control volume. So this is a dispersed phase which is not present at the boundary. So these surface forces will also be equal to 0. So that's why my dispersed phase momentum equation has only these three terms, only these two terms remaining in the equation. Okay, is this one clear? Now let me similarly write the momentum equation for continuous phase. When I am writing momentum equation for continuous phase, then continuous phase I already told you that this is nothing but a stagnant liquid. So if this is a stagnant liquid, then what will be forces? Acceleration will be 0. So left hand side is 0. In the right hand side I will be having body force. Body force is 1 minus alpha times rho c into gk. Then what I will be having? Interaction force. Interaction force on continuous phase because of the dispersed phase. Dispersed phase will also apply some interaction. So that is FCK. And then, because now I am talking about the continuous phase, so I will be having the stresses, yes, surface forces at the boundary of the. So surface forces are accounted for by using this term, sigma CK I. All are clear with this idea? Now I only have a two-phase system. So because of the two-phase system, FDK has to be equal to, or I should say FCK has to be equal to minus of FDK, which will be equal to minus of alpha rho d into GK. Is this point clear? All are clear with this point? Now, so my FCK is nothing but minus alpha rho d into GK. Now, one interesting fact is this sigma CK is actually accounting for both pressure force as well as the sigma dash CKI, deviatoric stress. If I consider my fluid is stagnant, then deviatoric stress will be equal to, deviatoric stress comes because of the rate of shear strain of the fluid element. So if my liquid is stagnant, then there will not be any rate of shear strain. So that's why sigma dash CW will be equal to 0. So it means in this sigma CKI, I will be only having the sole contribution of the pressure force. So this term I can simply replace here with what? I can simply replace with del P by del X K. Okay, kth direction because we are writing. So del P by del X K. Now what I can do, I can write this 0 equal to del P by del X K plus 1 minus alpha rho C G K plus what it has become FCK. FCK is nothing but minus of FDK. Sorry, not minus, it will be positive because FDK is minus alpha rho D G. So it will be plus. So in place of FCK, I can write alpha times rho D into G. Okay. So ultimately what I will be getting from here, del P by del XK is nothing but equal to 1 minus alpha into rho C plus alpha into rho D. What is this? GK I can take common. What is this? Mixture density rho. Okay, alpha times rho D plus 1 minus alpha times rho C. So volume fraction multiplied by individual phase densities. This is nothing but the mixture density. So it means del P by del XK will be equal to simply minus of rho GK, where rho is nothing but mixture density. Is this point clear? All are clear with this idea? Yes. So it means that whenever your particles are falling at the constant velocity, then your weight of particles, what is this? This is the weight of the fluid. So weight of fluid is balanced by the hydrostatic force acting because of the fluid. Then only these are moving at the constant velocity. Because if these forces are not same, then there will be acceleration of the particles. So if you have a stagnant fluid, so in a stagnant fluid when particles are falling, particles will fall under the effect of hydrostatic pressure. It means whatever their weight is, that weight is balanced by the hydrostatic pressure because of which they are falling at the constant velocity. Okay, if their weight is more than hydrostatic pressure, then they will be accelerating. If their weight is less, then they will be floating. So that is the reason. So they will be only freely falling under the uniform condition when their weight is balanced by the hydrostatic pressure. So that is mathematically also we have seen. Okay, if we do the algebraic manipulations between the dispersed phase and the continuous phase, then we can actually obtain this. So likewise, you can expect in your exam that some situation is given, there you have to apply the necessary conditions based on the physical inferences written in that condition. So for example, in this condition it was given that freely falling at constant velocity, uniform flow. So you have to now infer that acceleration has to be considered equal to 0. Then accordingly you need to tweak these equations and then come to the final solution. Is this one clear? All are clear with this idea? So this is application. Okay. So that is what I told you, what I have described you, actually same thing. I don't know why this is not working, but same equation I have copied over here. So FDK is equal to minus FCK, which is minus alpha rho d gk, and del P by del xk is equal to rho gk. So here I have written the final form directly, but here I have shown the derivation. Okay. Okay, now the way we have written this equation, continuity equation for a area averaged quantity, in the similar way I have written this momentum equation in terms of area averaged quantities. So whenever I will be using area averaged quantity, one area will be multiplied here, one area here will be in division, and of course when I am talking about the area averaged velocities, then I am not considering multiple directions. Now at entire cross section I have a single average value of the velocity. So that's why my u and I has become equal to u and k, which is written equal to u n. Okay, because in terms of area average quantity I am moving in the single direction. So that's why you can see over here this un square is written over here. Then minus delta n del p by del x, and then to account for the shear force. Now this shear stress should also act only in a single direction. So that's why it is written in the form of perimeter times tau w by area. So this is perimeter. P means perimeter of the cross section. Okay, whatever your cross section is there, the perimeter of that particular cross section is actually P times tau w by A. So this is the force because of the shear stress, and then you have this body force term, and then you have this interaction force term. So whenever this interaction force term and body force I am writing, I am specifically using x, means x is direction along the length of the channel. Okay, so this is area average momentum equation for dispersed phase or any individual phase. And if I do the summation of this, then this will be summation of these quantities, and this will be my area average thing. And of course when I am writing this in the summation form, then this delta n will go away, because ultimately continuous phase is already included in the summation one, and this interaction term will also become equal to 0. Okay. So this is the simplified version, because when you are doing area averaging, then rho n into alpha n can be written as rho. So mixture density times u, and A rho mixture density times u square. Okay. So this is the simplified equation for 1D flows. Only thing you need to do is you need to substitute over here mixture density.
So इसके अंदर assumption ये है
Un is actually,
UI.
yes, ui is. Then you have dispersed phase momentum equation in the volume form. So if you know that volume of dispersed phase is Vd, okay, so you can write it dd by ddt of rho d Vd into udk. That is the total rate of change of dispersed phase. Okay, and this is Fk is all interaction forces acting on the dispersed phase in kth direction, and this is the body force. Of course, whenever you are writing for dispersed phase, then surface force will not come into picture. Okay. And then, so this is the definition of D. And this is our further splitting of this equation by considering rho d Vd as one parameter and ud as other parameter. If I use the separation of variables, then this is the first part, and second part will become udk into id by nd, and id by nd is coming nothing but from our previous lecture of number continuity equation. Okay, and this is Fk and this. Now from here I can also write this Fdk, force acting on dispersed phase. If I know the number density of the number of dispersed phase particle, then I can write this: if Fk is the force acting on one particle times number of particles present in the system. Okay? Is this point clear? How this has come? All are clear with this idea? Okay, let me stop at this point. And this is nothing but our simply the disperse phase momentum equation. This is not applicable for other configurations. This will be applicable only when we are talking about the disperse phase. Okay?
same force radius सारे particles.
If we are considering the particles of uniform shape at the moment. But when particles are deformable, then it will be different. At the moment we are considering.
Surface plane.
This is the force in kth direction on a single particle.